SLS is the foundation to the journey to Mars. We carry more payload than any other rocket. The way that we did that is our rocket is extremely large. We have a lot of propellant in it. I just think that's amazing. It's so exciting. It's definitely a dream job for an aerospace engineer, I think. I do a lot of yoga. I teach yoga and own a yoga studio. They seem like they're very different, but they're definitely related. It's most exciting things I think that people do, right, is to develop a way for us to fly. We're not birds. We're not meant to fly, but we figured out a way.
Hello and welcome to Watch This Space. I'm Jim Bridenstine, the NASA Administrator, and today we're going to talk about the James Webb Space Scientist on the James Webb Space Telescope, and Dr. Thomas Zurbuchen, Associate Administrator of the Science Mission Directorate here at NASA. Gentlemen, thank you so much for joining me today.
Glad to be here.
Glad to be here.
Awesome. So Dr. Mather, tell me from your perspective, you're going to be the Senior Project Scientist on the James Webb Space Telescope. How excited are you about this mission and why?
It is the most exciting thing I could possibly imagine to be working on. It is the successor for the Hubble Space Telescope, and it will be far more powerful and much larger and be able to see things the Hubble could never see.
Is that right?
So it can see things the Hubble could not see because it's larger and because it picks up infrared light, which the Hubble cannot do. So infrared light comes from things that are too cool to emit visible light. So you're emitting infrared light, and so we're building a telescope that could see a bumblebee at the distance of the moon just from the heat that the bumblebee gives off.
So this enables us, in the infrared electromagnetic spectrum, this enables us to see potentially stars from a very, very long time ago. Obviously stars that wouldn't even exist today. But their wavelength, as it has traveled towards the Earth, the wavelength has expanded, and so it's in a different part of the electromagnetic spectrum, and that's what we're going to be able to see.
That's a big part of it. We see the most distant galaxies we can possibly imagine finding. We're looking for the very first ones that formed after the big expansion of the universe began. We call it the Big Bang, and then what happened after that? The galaxies were formed, but we don't know how.
Dr. Thomas Zurbuchen, you're the Associate Administrator of the Science Mission Directorate, so you have responsibility over this program as well as so many others. Share with us, going back in time, how James Webb came into being ultimately as a program, and where you see it going in the future.
The questions that John just addressed are questions that have been with us for many, many decades. And the telescope, of course, came into being after, I would say, the success of Hubble, which really I would say is, without Hubble, there's no Webb, right? It's a magnificent telescope that still is the most productive science machine that we have up there. Close to 1,000 publications a year come from that one telescope. It's just out of any other realm. I mean, it's just so amazing. So basically what happened, something like 2 decades ago, scientists came together as part of the national academies and basically said, like, what would be the next big telescope? And they imagined Webb, which, as John said, is important for 2 reasons. The first one is it's cold. The second one is it's big. and those 2 characteristics really drove Webb and of course started a process that let it evolve to where we are today with a telescope in which basically all parts are built, right, and we're in integration and test.
So tell me, how complex of a spacecraft is this, and how complex of a scientific instrument is on board?
I'm going to talk about the spacecraft. I'll let you talk about the instrument. And the spacecraft is complex for 2 reasons. The first one is that it's a deployed mirror, right? So because the whole thing unfurls like some origami type structure, and then is put in place very, very accurately.
So tell me this origami type structure, you're talking about the spacecraft itself. Why does it need to be, what is the origami type structure for?
So imagine that the mirror itself, it's 6.5 meters, that the thermal protection shield, which again is there to cool everything down, is the area of a tennis court. So there is no rocket where that fits in.
So the thermal protection shield, just for the audience, we're talking about something that blocks the sun so that ultimately we can have the absolute coldest mirror possible to detect the heat signature from infrared.
Absolutely. It blocks the sun 5 times over. That's how many such tennis courts we're deploying. Kind of small aluminum foils that are out there deployed and, out in space doing exactly what you said.
Okay, awesome. So that's complex in itself.
Oh, God, it is.
How many moving parts in order to deploy that?
Well, I mean, there's between 300 and 350 single points that move or kind of deploy in one fashion or another for this to occur.
Okay, and every single one of them has to work perfectly in order for this to deploy appropriately.
The vast majority of them, some of these, something like 50 or so, if they don't work, we can work around this. The others, yes, they have to work. So in other words, you can't just have a half-deployed tennis court out there. It's really hard. It's really hard to actually fly the spacecraft, and it would not become as cold as it needs to be.
Okay. As far as the scientific instruments on board, how complex are those and the challenges that we have?
Well, they're very complex. What makes them especially difficult is they have to be cold also. Some of them run at 7 degrees Kelvin, very close to the absolute zero, and some of them at 40 degrees Kelvin, also very cold. So this is something that we can do, but it's not familiar.
So Dr. Zurbuchen, tell us where are we right now with James Webb, and what can we expect as far as when are we going to see the first science from it, and ultimately when can the public be inspired by it?
So the good news is all the parts of the telescope are basically built. They're standing in California in one company all together and are being integrated and tested. And we're right now kind of in the test program of the spacecraft. That tennis courts on, all this, the sun shield, all these things we're testing right now and are basically doing everything we need to do. Cooling, we're shaking it, we're blasting sound at it to make sure it can survive launch and so forth. Right afterwards, the telescope, Otis, the instruments and the telescope are being integrated with the spacecraft, and then the whole test program, or a subset thereof, starts again, and we make sure that this entire spacecraft with its instruments can actually survive launch and can be deployed, and then we ship it and get it to space, and if everything goes well, kind of in 21, it's out there and it starts deploying over a time period.
About 2 weeks.
Yeah, John and I will be very nervous at that time period because we're going to get data back on the ground about all these single points, all these little puffs that make sure that this, this sun shield deploys, that everything goes just like planned.
As much as we've invested into this critically important scientific instrument, we have to get it complete. And my understanding is we're on the 5-yard line. And as you mentioned, all of the components are built. All we got to do now is punch it into the end zone. We're all very excited about that. How confident are you that the new schedule that we're going to lay out, which says that we're going to launch in March of 2021, how confident are you that we're going to be able to accomplish that?
I am confident that this schedule is precisely sufficient, and also the funding that we have allocated is sufficient to get us over the finish line, like you said. We have to execute. We have the team. We have independent voices that have told us this is what it takes. This is sufficient. We have done exactly that. And now it's a matter of, lining up the team, like you said, and carrying that ball. We
probably were excessively optimistic on how the integration and testing was going to go. The sun shield proved to be very complex and